the universe were an ocean, Earth wouldn't even be a single drop of water. It would be one atom inside that drop. The nearest star to our sun is 25 trillion miles away. That's so far that if you could travel at the speed of light, it would still take you over 4 years to get there. And that's just our cosmic neighbor. Our galaxy contains 400 billion stars. And there are 2 trillion more galaxies we can see, each with hundreds of billions of stars of their own. But here's what will absolutely blow your mind. Everything we can see, all those galaxies, all those stars, is just the tiniest fraction of what's really out there. Today, you're about to discover the true size of our universe, and trust me, by the end of this, you'll never look at the night sky the same way again. If you're curious about these cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. Your support is my biggest fuel to keep making this content. And one quick question. If you could instantly teleport to any location in the universe right now, where would you go? Let me know in the comments down below. I will choose the most creative answer. Now let's begin. Humans have always looked up at the night sky and wondered about the true size of everything out there. Ancient civilizations thought the stars were just lights attached to a celestial sphere, maybe a few hundred miles above Earth. They had no idea that each point of light was a sun, potentially with its own planets, separated by distances so vast that our minds simply can't grasp them. Today, thanks to incredible telescopes like Hubble, the James Webb Space Telescope, and ground-based observatories around the world, we've mapped the universe to distances that would have seemed like fantasy just a century ago. But here's the thing. The more we discover, the more we realize how much bigger everything is than we ever imagined. And if you want to dive even deeper into the true size and wonders of the universe, I highly recommend the book called Welcome to the Universe, an Astrophysical Tour by Neil deGrasse Tyson. It's a fascinating, beautifully written book that brings the cosmos to life and will change how you see the night sky forever. The link is in the description and pinned on the comments. Earth has a diameter of about 12,742 kilometers. That might sound big, but you could fit Earth inside Jupiter over 1,300 times. And Jupiter, you could fit it inside the Sun almost 1,000 times. Already we're dealing with scales that challenge our everyday experience. But the Sun, as massive as it is just an average star. There are stars out there like UY Scuti that are so large, if you placed one where our Sun is, its surface would extend beyond the orbit of Jupiter. That's a star so big that light itself takes hours to travel from one side to the other. Now let's zoom out further. Our solar system, including all the planets and the distant Oort cloud where comets come from, stretches about 2 light years across. A light year, the distance light travels in 1 year, is about 9.5 trillion kilometers. Try to imagine that distance. You can't really. Our brains didn't evolve to comprehend such scales. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object. It's been traveling for over 46 years at about 17 kilometers per second, and it's only about 23 billion kilometers from Earth. At that speed, it would take Voyager about 70,000 years to reach the nearest star, Proxima Centauri, which is 4.24 light-years away. Our Milky Way galaxy contains between 200 and 400 billion stars. If you tried to count them at 1 star per second, it would take you over 12,000 years to count them all. And each of these stars is separated by an average of about 5 light-years from its neighbors. The Milky Way itself is about 100,000 light-years across. To put that in perspective, when light left one side of our galaxy, humans hadn't even evolved yet. The largest member of our local group is the Andromeda Galaxy, located about 2.5 million light-years away. When you look at Andromeda through a telescope, you're seeing it as it was when the earliest human ancestors were just beginning to use stone tools. The local group itself is about 10 million light-years across, but even this is just a tiny corner of the universe. The local group is part of the Virgo supercluster, which contains over 1,000 galaxies and spans 110 million light-years. In 2014, astronomers discovered that even the Virgo supercluster is just a small part of an even larger structure called Laniakea, which means immense heaven in Hawaiian. Laniakea contains about 100,000 galaxies and stretches 520 million light-years across. It's a gravitationally bound structure so large that it takes light, the fastest thing in the universe, over 500 million years to cross it. But we're still just getting started on our journey through the cosmic scales. Recent observations from the Sloan Digital Sky Survey have revealed structures even larger than superclusters. The Sloan Great Wall, discovered in 2003, is a giant wall of galaxies stretching 1.37 billion light-years across. That's about 1/60th the diameter of the observable universe. Think about that for a moment. There are structures in our universe so large that they span significant fractions of everything we can see. These cosmic walls and filaments form a vast cosmic web with galaxies strung along them like dewdrops on a spider's web, and enormous voids between them containing almost no galaxies at all. The Hercules Corona Borealis Great Wall, discovered in 2013, is even larger. This structure is so vast that it challenges our understanding of how the universe could have formed such large structures in the time since the Big Bang. It stretches about 10 billion light-years across, more than 1/10 the diameter of the observable universe. But what exactly do we mean by the observable universe? This is a crucial concept that often gets misunderstood. The observable universe isn't the entire universe, it's just the part we can see. And the reason we can't see beyond it isn't because our telescopes aren't powerful enough. It's because of the fundamental nature of light and time. The universe began about 13.8 billion years ago with the Big Bang. This means that light from the most distant objects has had only 13.8 billion years to reach us. We can't see anything farther away than the distance light could have traveled in that time. It's like standing in the middle of a foggy field. You can only see so far in any direction, not because the field ends there, but because that's the limit of your vision. But here's where it gets even more interesting. Because the universe has been expanding all this time, the most distant objects we can see are now much farther away than 13.8 billion light-years. The light we see from them has been traveling toward us while space itself has been stretching, carrying those objects even farther away. When we account for this expansion, the current distance to the edge of the observable universe is about 46.5 billion light-years in any direction. That means the observable universe is about 93 billion light-years in diameter. Try to wrap your mind around that. 93 billion light-years across. To help visualize this, let's use another analogy. If the Earth were shrunk down to the size of a grain of sand, the observable universe would still be about 37,000 kilometers across, almost the circumference of Earth at its actual size. Every time we try to scale things down to comprehensible sizes, the universe fights back with its sheer immensity. The James Webb Space Telescope, launched in 2021, has pushed our vision even closer to the edge of the observable universe. It has detected galaxies that existed just a few 100 million years after the Big Bang, their light having traveled for over 13 billion years to reach us each. These ancient galaxies appear as tiny red smudges in the telescope's images, but each one contains billions of stars. One of the most humbling realizations is that every point in space has its own observable universe. An alien civilization in a galaxy 10 billion light-years away would see a completely different set of galaxies at the edge of their observable universe. There are parts of the universe that they can see that we never will, and vice versa. The universe is so vast that different observers literally cannot see all of the same things. Now here's something that will really challenge your understanding of reality. The universe isn't just big, it's getting bigger every second. And I don't mean that galaxies are flying apart through space like shrapnel from an explosion. Space itself is expanding, stretching like a cosmic fabric, carrying galaxies along for the ride. This discovery completely revolutionized our understanding of the cosmos. In 1929, Edwin Hubble made observations at Mount Wilson Observatory that changed everything. He noticed that almost all galaxies were moving away from us, and the farther away they were, the faster they appeared to be receding. This wasn't because we're at the center of some cosmic explosion, it's because space everywhere is expanding. Imagine drawing dots on a balloon and then inflating it. As the balloon expands, every dot moves away from every other dot. A dot on the opposite side of the balloon moves away faster than a nearby dot, not because it's traveling faster through the balloon's surface, but because there's more balloon expanding between you and the distant dot. That's exactly what's happening with galaxies in our universe. The rate of this expansion is described by something called the Hubble constant, currently measured at about 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. This means that for every megaparsec of distance between us and a galaxy, that galaxy appears to be moving away from us at an additional 70 kilometers per second. Let's put this in perspective. A galaxy 1 megaparsec away is receding at 70 kilometers per second. A galaxy 10 megaparsecs away is receding at 700 kilometers per second. A galaxy 1,000 megaparsecs away is receding at 70,000 kilometers per second, nearly a quarter the speed of light. But here's where things get truly mind-bending. At a certain distance, galaxies are receding from us faster than the speed of light. Wait, you might think, doesn't Einstein's theory of relativity say nothing can travel faster than light? That's true. Nothing can travel through space faster than light. But space itself can expand at any rate it wants. The galaxies aren't breaking any cosmic speed limits, they're just being carried along by the expanding space between us and them. This creates what we call the cosmic event horizon. Beyond a certain distance, about 16 billion light-years away, galaxies are receding so fast that light emitted from them today will never reach us. Ever. No matter how long we wait, no matter how powerful our telescopes become, we will never see the light that those galaxies are emitting right now. And speaking of things that seem impossible, galaxies moving faster than light is just the beginning. The universe is packed with objects that appear to break the rules of physics as we know them. I'm talking about stars that are older than the universe itself, planets so dark they absorb 99% of light that hits them, and cosmic structures so large they challenge our theories of how the universe formed. If you're fascinated by these mind-bending discoveries, I've compiled 54 of the most impossible objects we've actually found in space in my video, called 54 Things That Shouldn't Exist in Space But Do. Trust me, some of these discoveries make even the expanding universe seem normal by comparison. Check it out after this video. The link is in the description and on the card above. Now let's continue. There are events happening in the universe right now, stars being born, civilizations perhaps rising and falling, that we will never ever know about. They are forever beyond our cosmic horizon, as unreachable as if they existed in another universe entirely. But it gets even stranger. Remember those distant galaxies we can see, the ones whose light has been traveling for billions of years? By the time their light reaches us, they've moved much farther away due to the expansion of space. Some of the most distant galaxies we can see are now over 30 billion light-years away, even though we're seeing them as they were when the universe was much younger and smaller. The cosmic microwave background, or CMB, gives us a snapshot of the universe when it was only 380,000 years old. This faint radiation fills the entire sky and represents the oldest light we can see. When this light was emitted, the matter that produced it was only about 42 million light-years away from the matter that would eventually become our galaxy. But due to 13.8 billion years of expansion, that same matter is now about 46 billion light-years away, at the very edge of our observable universe. The Planck satellite, launched by the European Space Agency in 2009, mapped the CMB with unprecedented precision. The data revealed tiny temperature fluctuations, differences of just a few parts in 100,000, that represent the seeds of all cosmic structure. These minute variations in density eventually grew into the galaxies, stars, and planets we see today. But here's a sobering thought: the expansion of the universe is accelerating. In 1998, two independent teams studying distant supernovae made a shocking discovery. They expected to find that the expansion of the universe was slowing down due to gravity. Instead, they found it was speeding up. This discovery earned the team leaders the 2011 Nobel Prize in Physics. The cause of this acceleration is one of the biggest mysteries in science. We call it dark energy, but that's really just a label for our ignorance. Dark energy makes up about 68% of the total energy density of the universe, yet we have no idea what it actually is. All we know is that it's causing space to expand faster and faster. This accelerating expansion has profound implications for the future of the universe. As time goes on, galaxies will recede from us faster and faster. Eventually, all galaxies outside our local group will disappear beyond our cosmic horizon. The local group itself will merge into a single, giant galaxy, sometimes called Milkomeda, when the Milky Way and Andromeda collide in about 4.5 billion years. In the far distant future, perhaps 100 billion years from now, any civilizations that arise will look out into space and see only their own galaxy. The cosmic microwave background will have been stretched to wavelengths too long to detect. They'll have no direct evidence of the Big Bang, no other galaxies to observe, no way to know about the vast cosmos we can see today. The universe will have erased its own history. This is already happening on smaller scales. There are galaxies at the edge of our observable universe whose light is so redshifted, stretched by the expansion of space, that they're barely detectable even with our most powerful telescopes. The James Webb Space Telescope can see some of these extremely distant galaxies only because it observes in infrared light, where their visible light has been redshifted too. The expansion of space also affects our understanding of cosmic distances. When we say a galaxy is a certain number of light years away, which distance do we mean? The distance when the light was emitted? The distance right now? The distance when the light reaches us? These are all different values for distant objects, and they can differ by billions of light years. Cosmologists use several different distance measures to handle this complexity. There's the light travel time distance, how long the light has been traveling. There's the co-moving distance, the distance right now accounting for expansion. There's the angular diameter distance related to how large objects appear, and there's the luminosity distance related to how bright objects appear. For nearby objects, these are all similar, but for distant objects, they can be vastly different. The universe's expansion also creates what we call the particle horizon. This is the maximum distance from which particles could have traveled to us in the age of the universe. It defines the boundary of the observable universe and is currently about 46.5 billion light-years away. But this horizon is constantly growing as the universe ages and light from more distant regions has time to reach us. Interestingly, during the first fraction of a second after the Big Bang, the universe went through a period called cosmic inflation. During this incredibly brief time, lasting only about 10 to the negative 32 seconds, the universe expanded by a factor of at least 10 to the 26. That's a 1 followed by 26 zeros. A region smaller than a proton expanded to larger than a grapefruit almost instantaneously. This inflationary period solved several puzzles about the universe, including why it appears so uniform on large scales and why space appears to be geometrically flat. But it also means that the entire observable universe today originated from a tiny region of space that was causally connected before inflation. Everything we can see was once compressed into a volume smaller than an atom. The evidence for inflation comes from precise measurements of the cosmic microwave background. The patterns of temperature fluctuations match exactly what inflation theory predicts. These observations have been confirmed by multiple missions, including WMAP, Wilkinson Microwave Anisotropy Probe, and Planck, providing strong support for this remarkable period of exponential expansion. But inflation also implies something profound. Our observable universe is likely just a tiny fraction of a much larger whole. If inflation occurred, then the total universe could be vastly larger than what we can see, perhaps infinite. Our observable universe would be like a single drop of water in an ocean of unimaginable size. Some theories suggest that inflation might not have stopped everywhere at the same time. In this eternal inflation scenario, most of space is still inflating at an exponential rate, with only small pockets stopping to form universes like ours. This would create a multiverse, an infinite collection of pocket universes, each with potentially different physical properties. For nearby stars, we use a technique called parallax. Hold your finger in front of your face and close one eye, then the other. Notice how your finger appears to shift position against the background? That's parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring this tiny shift, we can calculate the star's distance using simple trigonometry. The European Space Agency's Gaia mission, launched in 2013, has revolutionized parallax measurements. This remarkable spacecraft has measured the positions and distances of over 1.8 billion stars with unprecedented precision. For the nearest stars, Gaia can measure distances accurate to within 0.1%, like measuring the distance from New York to Los Angeles to within a mile. But parallax only works for relatively nearby stars, out to about a few thousand light-years with current technology. Beyond that, the shifts become too small to measure accurately. So we need the next rung on our ladder, standard candles. A standard candle is any astronomical object whose true brightness, what astronomers call absolute magnitude, we know. If you know how bright something really is, and you measure how bright it appears from Earth, you can calculate its distance. It's like seeing a car's headlights at night. If you know how bright those headlights are, you can estimate how far away the car is based on how dim they appear. One type of standard candle is Cepheid variable stars. These stars pulsate, brightening and dimming in a regular pattern. In 1912, Henrietta Swan Leavitt discovered that the period of pulsation is directly related to the star's true brightness. Measure the period, and you know the brightness. Measure how bright it appears from Earth, and you can calculate its distance. Cepheids are bright enough to be seen in nearby galaxies, allowing us to measure distances up to about 100 million light-years. Edwin Hubble used Cepheids to prove that Andromeda was a separate galaxy far outside our Milky Way, settling the great debate about whether spiral nebulae were within our galaxy or separate island universes. But even Cepheids have their limits. For more distant galaxies, we need even brighter standard candles. Enter Type Ia supernovae, the nuclear explosions of white dwarf stars. These cosmic firecrackers all explode with nearly the same brightness, making them visible across billions of light-years. When a white dwarf in a binary system steals enough matter from its companion star to exceed 1.4 times the mass of our Sun, called the Chandrasekhar limit, it undergoes a catastrophic thermonuclear explosion. The physics of this process means that all Type Ia supernovae have nearly identical peak brightness, about 5 billion times brighter than our Sun. The Supernova Cosmology Project and the High-Z Supernova Search Team used these cosmic beacons to discover that the universe's expansion is accelerating. By comparing the apparent brightness of distant supernovae with their redshift, how much their light has been stretched by cosmic expansion, they could map out the expansion history of the universe. But measuring cosmic distances isn't just about brightness. We also use the redshift of light itself. As space expands, it stretches the wavelength of light traveling through it. This cosmic redshift is directly related to how much the universe has expanded since the light was emitted. For very distant objects, redshift becomes our primary distance indicator. The most distant galaxies discovered by the James Webb Space Telescope have redshifts greater than 13, meaning the universe has expanded by a factor of 14 since their light was emitted. These galaxies are so far away that their ultraviolet and visible light has been stretched all the way into the infrared. The Sloan Digital Sky Survey has measured redshifts for millions of galaxies, creating the most detailed three-dimensional map of the universe ever made. This cosmic cartography reveals the large-scale structure of the universe, the cosmic web of galaxy clusters, filaments, and voids that stretches across billions of light years. But there's a catch with using redshift for distance. The relationship between redshift and distance depends on the expansion history of the universe, which in turn depends on the amounts of matter, radiation, and dark energy. This is why measuring distances and understanding cosmology go hand in hand. Each informs the other. Another powerful technique uses baryon acoustic oscillations, or BAO. In the early universe, sound waves propagated through the hot plasma of protons, electrons, and photons. When the universe cooled enough for atoms to form, these sound waves froze in place, creating a characteristic scale about 490 million light-years in the distribution of galaxies. This cosmic ruler appears in galaxy surveys as a slight excess of galaxy pairs separated by this characteristic distance. By measuring how this scale appears at different redshifts, astronomers can trace the expansion history of the universe with remarkable precision. The Dark Energy Survey and other projects have used BAO to confirm and refine our understanding of cosmic acceleration. For the very largest scales, we use the cosmic microwave background itself. The CMB contains a wealth of distance information encoded in its temperature fluctuations. The angular size of these fluctuations tells us about the geometry of space and the total content of the universe. Combined with other measurements, the CMB provides our most precise constraints on cosmic distances and the age of the universe. The Atacama Cosmology Telescope and the South Pole Telescope have mapped the CMB from the ground with incredible detail, complementing space-based observations. These measurements have determined the age of the universe to be 13.797 billion years, with an uncertainty of only 21 million years, a precision of better than 0.2%. But measuring cosmic distances isn't without controversy. Different methods sometimes give slightly different results, leading to what's known as the Hubble tension. Local measurements using Cepheids and supernovae give a Hubble constant of about 73 kilometers per second per megaparsec, while CMB measurements give about 67. This discrepancy might be telling us something profound about the universe. Perhaps that dark energy changes with time, or that there's new physics we don't yet understand. The James Webb Space Telescope is helping to resolve this tension by providing more precise measurements of Cepheids and other distance indicators in distant galaxies. Its infrared vision can peer through cosmic dust that obscures visible light, giving us clearer views of these cosmic milestones. Gravitational lensing provides another way to probe cosmic distances. When light from a distant galaxy passes near a massive object like a galaxy cluster, the cluster's gravity bends the light, creating multiple images or distorted arcs. The geometry of these lensed images depends on the distances to both the lens and the background source. The Hubble Space Telescope has discovered thousands of gravitational lenses, each one a cosmic laboratory for measuring distances and testing our understanding of gravity. Some lensed quasars show time delays between their multiple images. When the quasar brightens, we see the change in different images at different times. These time delays provide yet another way to measure cosmic distances and the Hubble constant. Future telescopes will push our distance measurements even further. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will discover thousands of Type Ia supernovae, mapping the expansion history of the universe with unprecedented detail. The Vera Rubin Observatory will survey the entire southern sky every few nights, discovering millions of distant galaxies and tracking how cosmic structure evolves over time. The European Space Agency's Euclid mission, launched in 2023, is designed specifically to study dark energy by measuring the distances and shapes of billions of galaxies. By combining multiple distance indicators, galaxy clustering, weak gravitational lensing, and baryon acoustic oscillations, Euclid will create the most detailed three-dimensional map of the universe ever made. When you look up at the night sky, the stars seem randomly scattered across the darkness. But zoom out to cosmic scales, and a breathtaking pattern emerges. Galaxies aren't distributed evenly throughout space. They form an intricate cosmic web with dense clusters connected by filaments surrounding vast empty voids. This structure tells the story of how gravity has sculpted matter over billions of years, creating the largest patterns in nature. The discovery of this cosmic web is one of the great detective stories in astronomy. In the 1970s and 80s, astronomers began the painstaking work of mapping galaxy positions in 3 dimensions. What they found shocked them. Instead of a random distribution, galaxies formed sheets, walls, and filaments, with enormous empty regions between them. The first hint came from the CFA Redshift survey led by Margaret Geller and John Hoekra at the Harvard-Smithsonian Center for Astrophysics. By measuring the redshifts of thousands of galaxies, they created the first slice of the universe, a map showing galaxy positions in a wedge of sky. The result looked like a cross-section of soap bubbles, with galaxies outlining the bubble walls and vast voids in between. One of the most striking features they discovered was the CFA Great Wall, a sheet of galaxies stretching over 500 million light-years across. At the time, it was the largest structure ever discovered, challenging theories about how such massive structures could form in the age of the universe. But this was just the beginning. As surveys grew larger and technology improved, even more enormous structures emerged. The Sloan Great Wall, discovered in 2003, stretches 1.37 billion light-years across. The Boss Great Wall, found in 2016, spans about 1 billion light-years. These structures are so large that they contain millions of galaxies, each with hundreds of billions of stars. The voids between these structures are equally impressive. The Boötes supervoid, also called the Great Nothing, is a roughly spherical region about 330 million light-years in diameter that contains very few galaxies. If the Milky Way were in the center of this void, we wouldn't have discovered other galaxies until the 1960s, when telescopes became powerful enough to see across the entire void. But perhaps the most mind-bending discovery is that these structures, the walls, filaments, and voids, form a pattern that repeats on the largest scales. The universe looks roughly the same no matter where you are or which direction you look, once you average over scales larger than about 300 million light-years. Cosmologists call this the cosmological principle, and it's a fundamental assumption in our models of the universe. The formation of this cosmic web is a beautiful example of how gravity works on the largest scales. In the early universe, matter was distributed almost perfectly evenly, with tiny density fluctuations of only about 1 part in 100,000. But gravity is relentless. Regions that were slightly denser than average attracted more matter, growing denser still. Regions that were slightly less dense lost matter to their denser neighbors, becoming ever emptier. Computer simulations like the Millennium Simulation and the Illustris project have recreated this process in stunning detail. Starting from the tiny fluctuations seen in the cosmic microwave background, these simulations use the laws of physics to evolve the universe forward in time. The results match the observed cosmic web with remarkable accuracy, confirming our understanding of structure formation. Dark matter plays a crucial role in forming the cosmic web. This mysterious substance, which makes up about 27% of the universe, doesn't emit, absorb, or reflect light, but it does have gravity. Dark matter started clumping earlier than ordinary matter because it doesn't interact with radiation. These dark matter clumps provided the gravitational seeds around which ordinary matter could later accumulate to form galaxies. The bullet cluster provides dramatic evidence for dark matter's role in cosmic structure. This system consists of 2 galaxy clusters that collided about 150 million years ago. The hot gas between galaxies, visible in X-rays, was slowed by the collision, but the dark matter, detected through gravitational lensing, passed right through. This separation of ordinary and dark matter is some of the strongest evidence that dark matter really exists. The cosmic web isn't static, it's constantly evolving. Galaxy clusters grow by merging with other clusters and by accreting matter from the filaments that connect them. The Virgo cluster, our local supercluster's heart, is currently pulling in galaxies from millions of light-years around, including our own local group. In about 100 billion years, all these galaxies will have merged into a single, giant elliptical galaxy. The filaments themselves are like cosmic highways. Galaxies and gas flow along these filaments toward the clusters at their intersections. The MUSE instrument on the Very Large Telescope has actually detected this cosmic gas flow, seeing hydrogen gas streaming along filaments and feeding the growth of galaxies. It's like watching the universe's circulatory system in action. Recent discoveries have revealed that the cosmic web is even more complex than we thought. Using the light from distant quasars as cosmic flashlights, astronomers can detect gas in the filaments through absorption lines. This technique, called the Lyman alpha forest, reveals that the cosmic web extends down to much smaller scales than we can see in galaxy surveys. The Dark Energy Survey, which completed observations in 2019, mapped 300 million galaxies across 1/8 of the sky. This massive dataset reveals the cosmic web in unprecedented detail, showing how dark energy affects structure formation. As dark energy accelerates cosmic expansion, it's gradually shutting down the formation of new structures. The cosmic web we see today is nearly the final version. Few new large structures will form in the future. But the cosmic web holds mysteries we're still trying to solve. The distribution of galaxies shows subtle patterns that might hold clues to the universe's earliest moments. Baryon acoustic oscillations, the frozen sound waves from the early universe, create a characteristic scale in galaxy clustering. Primordial non-Gaussianity, tiny deviations from perfect randomness in the initial fluctuations, would leave distinctive signatures in the largest structures. The Euclid Space Telescope and the Vera Rubin Observatory are designed to map the cosmic web with unprecedented precision. By measuring the positions and shapes of billions of galaxies, these surveys will test our theories of gravity on the largest scales and search for signs of new physics. One of the most exciting frontiers is studying the warm, hot, intergalactic medium, the gas in filaments that's too cool to emit X-rays but too hot to form stars. This gas contains most of the ordinary matter in the universe, but it's incredibly difficult to detect. Future X-ray telescopes like Athena will finally map this hidden component of the cosmic web. The cosmic web also affects how we see the universe. Gravitational lensing by the web's mass distorts the shapes of distant galaxies, an effect called cosmic shear. By measuring these tiny distortions across millions of galaxies, astronomers can map the distribution of dark matter throughout the cosmic web, seeing structure that would otherwise be invisible. Perhaps most remarkably, the cosmic web connects us to the universe's largest scales. The atoms in your body have been on an incredible journey, forged in the hearts of stars, blown into space by supernovae. They've traveled along the cosmic web's filaments, been incorporated into new stars and planets, and eventually became part of you. You are literally made of cosmic web material, connected to structures spanning billions of light years. The cosmic web also shapes the universe's future. As dark energy continues to accelerate expansion, the web will gradually dissolve. Clusters will become isolated islands in an ever emptier universe. The filaments will stretch and fade. Billions of years from now, the beautiful patterns we see today will be gone, replaced by a cold, empty cosmos with only isolated galaxy clusters remaining. But for now, we live in the cosmic web's golden age. We can see its full glory spread across the sky, from the smallest filaments to the greatest walls. Every galaxy we observe, every cluster we map, adds another piece to our understanding of the largest patterns in nature. The cosmic web is the universe's masterpiece, painted with galaxies across the canvas of space and time. Here's a thought that should make you feel both incredibly small and part of something unimaginably vast. Everything we've talked about so far, every galaxy, every cluster, every cosmic structure, exists only within our observable universe. But the actual universe, the total universe, is almost certainly far, far larger. It might even be infinite. Remember, the observable universe is limited by the speed of light and the age of the universe. We can only see objects whose light has had time to reach us in the 13.8 billion years since the Big Bang. But there's no reason to think the universe ends at this horizon. In fact, everything we know about physics suggests it continues far beyond what we can see. Think of it this way. Imagine you're standing in a thick fog. You can only see about 50 feet in any direction. Does the world end at that 50-foot boundary? Of course not. The fog just limits your vision. The cosmic horizon is similar. It's a limit on our vision, not an edge to the universe itself. The cosmic microwave background gives us strong evidence that the universe extends far beyond our observable horizon. The CMB is remarkably uniform in all directions, with temperature variations of only about 1 part in 100,000. This uniformity would be impossible if the universe ended at our observable horizon. We'd expect to see edge effects or asymmetries. Furthermore, the universe appears to be geometrically flat to within about 0.4% accuracy. In a flat universe, parallel lines never meet, and the angles of a triangle add up to exactly 180 degrees. But for the universe to be this flat, it must be either infinite or at least vastly larger than the observable universe. If the total universe were only slightly larger than what we can see, we'd detect curvature. So how big is the total universe? The honest answer is, we don't know. It could be just slightly larger than the observable universe, or it could be millions of times larger, or it could be truly infinite. Current observations only tell us that it must be at least 250 times larger than the observable universe in diameter. That means the volume of the total universe is at least 15 million times larger than what we can see. But many cosmologists suspect the universe is actually infinite. The simplest models of cosmic inflation naturally produce an infinite universe. During inflation, an incredibly tiny region of space expanded exponentially, becoming vastly larger than our observable universe. If the pre-inflation universe was infinite, or even just very large, then the post-inflation universe would be infinite too. An infinite universe leads to some mind-bending implications. In an infinite universe with a finite number of possible quantum states, everything that can happen must happen somewhere. There would be an infinite number of galaxies, stars, and planets. Statistically, there would even be exact copies of Earth, complete with copies of you reading these exact words, somewhere out there in the infinite cosmos. In an infinite universe, these patterns must repeat, like how the infinite decimal expansion of pi must eventually contain every possible finite sequence of numbers. But even if the universe isn't infinite, what lies beyond our observable horizon is fascinating to contemplate. Right now, at this very moment, there are galaxies beyond our horizon that we cannot see. Light from these galaxies hasn't had time to reach us yet. Every day, the observable universe grows by about 160 million light-years in radius as light from more distant regions finally arrives. This means that tomorrow we'll be able to see galaxies that are invisible today. Of course, these newly visible galaxies will appear as they were 13.8 billion years ago when their light began its journey toward us. We're constantly seeing new parts of the universe's baby picture, even as those same regions have evolved into mature galaxies we'll never observe. The accelerating expansion of the universe adds another layer of complexity. Because of dark energy, there are galaxies whose light will never reach us no matter how long we wait. These galaxies are beyond our event horizon, not just temporarily invisible, but permanently disconnected from our observable universe. Currently, this event horizon is about 16 billion light-years away. Galaxies beyond this distance are receding from us faster than the speed of light due to cosmic expansion. Light emitted from these galaxies today will never reach us, no matter how long the universe exists. We're causally disconnected from these regions forever. This creates a poignant situation. Right now, we can see galaxies that are currently beyond our event horizon. We see them as they were billions of years ago when they were closer, and their light could still reach us. But the light they're emitting right now will never arrive. We're watching the last images of galaxies that are already lost to us forever. The multiverse hypothesis adds yet another layer to our cosmic perspective. Some theories of inflation suggest that our universe is just one bubble in an infinite foam of universes. Each bubble would have its own Big Bang, its own laws of physics, and its own cosmic history. The total multiverse would be infinitely larger than any single universe, including ours. In the eternal inflation scenario, most of space is still undergoing exponential inflation. Our universe is just a tiny pocket where inflation happened to stop, allowing matter and galaxies to form. But beyond our universe, inflation continues forever, constantly creating new pocket universes. The multiverse would be infinite and eternally growing. String theory suggests another type of multiverse, the landscape multiverse. String theory has about 10 to the 500 different possible solutions. each corresponding to a universe with different physical laws. If all these possibilities are realized somewhere, then our universe is just one of an incomprehensibly vast number of different universes, each with its own unique physics. Some physicists have proposed that black holes might create new universes. In this scenario, when matter collapses into a black hole, it might bounce and expand into a new universe, disconnected from the parent universe. Our own universe might have been born from a black hole in another universe. If true, universes would reproduce like living organisms, with successful universes, those that make many black holes, having more descendants. The many worlds interpretation of quantum mechanics suggests yet another type of multiverse. Every time a quantum measurement occurs, the universe splits into multiple branches, one for each possible outcome. This would create an exponentially growing tree of parallel universes, all slightly different from each other. In some branch, you decided not to read this article. In another, dinosaurs never went extinct, but how can we test these ideas about what lies beyond our observable universe? This is one of the biggest challenges in modern cosmology. By definition, we can't directly observe anything beyond our cosmic horizon, but we can look for indirect evidence. For example, if our universe collided with another bubble universe in the distant past, it might have left a circular pattern in the cosmic microwave background. Some researchers have searched for these collision signatures, though none have been definitively found. The lack of detected collisions places constraints on multiverse models. The distribution of physical constants in our universe might also provide clues. If the multiverse exists and different regions have different physics, then our observed constants should be typical for regions that can support observers. This anthropic reasoning is controversial, but might explain why constants like the cosmological constant have the values they do. Future observations might detect evidence of the universe beyond our horizon. Gravitational waves, ripples in space-time itself might carry information from beyond the electromagnetic horizon. Primordial gravitational waves from inflation could tell us about regions of the universe we'll never see with light. The implications of a universe, or multiverse, vastly larger than what we can observe, are profound. It means our entire observable universe, with its hundreds of billions of galaxies, might be an insignificantly tiny fraction of the whole. We're like microbes in a drop of water, unaware of the ocean surrounding us. Looking at the vastness of the universe naturally leads to a profound question. What happens next? Where is this enormous cosmos headed? The answer, based on our current understanding of dark energy and cosmic expansion, is both fascinating and sobering. The universe that seems so vibrant and full of activity today is heading toward a cold, empty, and lonely future, what cosmologists call the heat death of the universe. Let's start with what we know for certain. The universe is not only expanding, but that expansion is accelerating. Every galaxy outside our local group is moving away from us, and they're doing so faster every day. In about 4.5 billion years, our Milky Way will collide and merge with the Andromeda Galaxy, creating a giant elliptical galaxy sometimes called Milkomeda. But this will be one of the last major galaxy mergers we'll ever be part of. As dark energy continues to push galaxies apart, the night sky will gradually empty. In about 100 billion years, roughly 7 times the current age of the universe, all galaxies outside our local group will have passed beyond our cosmic event horizon. They'll be receding faster than light, making them forever invisible to us. Any civilizations alive at that time will see only their own galaxy surrounded by absolute darkness, but the story doesn't end there. Stars themselves are temporary phenomena. Our sun will die in about 5 billion years, first swelling into a red giant and then shrinking into a white dwarf. Larger stars die more quickly in spectacular supernova explosions. Smaller red dwarf stars can shine for trillions of years, but even they will eventually fade. New stars form from clouds of gas and dust, but this process won't continue forever. With each generation of stars, some matter gets locked away in stellar remnants, white dwarfs, neutron stars, and black holes. Some gas gets ejected from galaxies entirely. Eventually, perhaps in about 100 trillion years, galaxies will run out of gas to form new stars. The age of stars will end, and the universe will enter what's called the degenerate era. During the degenerate era, the universe will be dominated by stellar remnants. White dwarfs will slowly cool, taking about 10 to the 15th years to fade to black dwarfs, cold, dark spheres of degenerate matter. The universe will be a graveyard of dead stars, with no new ones being born to replace them. But even these stellar corpses aren't eternal. Given enough time, and the universe will have plenty of it, even solid matter isn't stable. Through an exotic process called quantum tunneling, protons might decay. The timescale for proton decay is uncertain, but it could be around 10 to the 34 years. If protons do decay, all ordinary matter in the universe will eventually dissolve into lighter particles like electrons and positrons. Black holes will outlive everything else, but even they aren't permanent. Stephen Hawking discovered that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to slowly evaporate. The process is incredibly slow. A black hole with the mass of our Sun would take about 10 to the 67 years to evaporate completely. Supermassive black holes like the ones at the centers of galaxies will last even longer. A black hole with 1 billion solar masses would take about 10 to the 98 years to evaporate. But eventually, even the largest black holes will disappear in bursts of radiation, leaving behind only elementary particles and photons. After the last black hole evaporates, the universe will enter the dark era. In this final epoch, the universe will contain only sparse elementary particles, electrons, positrons, neutrinos, and photons, separated by vast distances. These particles will occasionally meet and annihilate, producing faint flashes of light in an otherwise dark cosmos. The expansion of the universe will continue to dilute these particles, making encounters increasingly rare. The temperature of the universe will approach absolute zero, but never quite reach it. This is the heat death, not a universe destroyed by fire, but one that fades into cold, dark emptiness. The timescales we're discussing are so vast that they challenge comprehension. The current age of the universe, 13.8 billion years, is less than a blink compared to the trillions upon trillions of years the universe will exist. We live in the very early days of the cosmos, a brief moment when stars shine and life is possible. But could this fate be avoided? Some physicists have proposed alternatives. If dark energy isn't constant but changes over time, the universe's fate could be different. If dark energy weakens, the expansion might slow or even reverse, leading to a big crunch, where the universe collapses back on itself. If dark energy strengthens, it could lead to a big rip, where the expansion becomes so violent that it tears apart galaxies, stars, planets, and eventually even atoms. Current observations suggest dark energy is constant to within about 10%, favoring the heat death scenario. But we've only been measuring dark energy for about 25 years, a cosmic instant. Over billions of years, even tiny changes could dramatically alter the universe's fate. There's also the possibility of new physics we haven't discovered yet. Perhaps there are phase transitions in the vacuum of space that could restart cosmic inflation, creating new bubble universes. Maybe intelligent civilizations could find ways to create new universes or escape to them. These ideas are highly speculative, but in a universe that will exist for 10 to the 100 years or more, even unlikely events might occur. The concept of Boltzmann brains adds a bizarre twist to the far future. In an infinitely old universe, random quantum fluctuations could occasionally assemble particles into any configuration, including conscious observers. These Boltzmann brains would be far more numerous than biological observers, leading to strange philosophical questions about the nature of consciousness and observation. Some cosmologists have proposed that the universe might be cyclic. In these models, the universe goes through endless cycles of expansion and contraction, or parallel universes collide periodically, resetting the cosmos. Each cycle would be hundreds of billions or trillions of years long, but the universe as a whole would be eternal. Roger Penrose's conformal cyclic cosmology suggests that the infinitely expanded future of one universe becomes the Big Bang of the next. In this model, the heat death isn't the end but a transition to a new beginning. The universe would go through infinite cycles, each one called an aeon. But even if our universe is heading toward heat death, the journey there will be extraordinary. For trillions of years, there will still be stars, albeit dim red dwarfs. Civilizations could potentially survive by huddling around these faint suns or by extracting energy from black holes. The universe will be very different from today, but not necessarily lifeless. In fact, the far future might offer opportunities impossible today. As Freeman Dyson pointed out, if thinking can be instantiated in very low-energy processes, then life and intelligence might survive indefinitely, thinking slower and slower thoughts as the universe cools, but never quite stopping. The digital era offers another perspective. If consciousness can be uploaded to computers, and if these computers can operate at extremely low temperatures and energy levels, then civilizations might survive far longer than biological life ever could. They could slow down their subjective time to match the universe's evolution, experiencing eons of thought while consuming minimal energy. Black holes might serve as the ultimate cosmic repositories. Information that falls into a black hole might be preserved on its event horizon, according to the holographic principle. As black holes evaporate through Hawking radiation, this information would be released back into the universe, though in a highly scrambled form. Advanced civilizations might use black holes as vast information storage devices, preserving their knowledge for unimaginable lengths of time. The possibility of creating new universes offers perhaps the ultimate escape from heat death. If it's possible to trigger inflation in a small region of space, that region would expand into a new universe, disconnected from the parent. Civilizations might become cosmic gardeners, planting seeds for new universes before their own dies. Carl Sagan famously called Earth a pale blue dot, a mote of dust suspended in a sunbeam. From the Voyager 1 spacecraft over 6 billion kilometers away, Earth appears as a tiny point of light, less than a pixel in size. On that dot, every human who ever lived was born and died. Every triumph and tragedy, every empire and civilization, every species that ever evolved, all of it happened on that one tiny world. But rather than making us feel insignificant, this cosmic perspective reveals something profound about our existence. We are the universe becoming aware of itself. Through billions of years of cosmic evolution, from the Big Bang through the formation of galaxies, stars, and planets, matter organized itself into increasingly complex forms until it produced beings capable of contemplating their own existence and the cosmos that created them. Think about what had to happen for you to exist. First, the universe had to have exactly the right physical constants. If the strong nuclear force were just 2% stronger, protons would stick together and there would be no hydrogen, and therefore no stars like our sun. If it were 5% weaker, hydrogen would be the only element, with no carbon, oxygen, or other elements necessary for life. Then about 9 billion years after the Big Bang, in an unremarkable spiral arm of an ordinary galaxy, a cloud of gas and dust collapsed to form our Sun and its planets. Earth formed at exactly the right distance, not too hot, not too cold, for liquid water to exist on its surface. The collision that created our Moon also stabilized Earth's rotation, giving us regular seasons and a stable climate. For nearly 1 billion years, Earth was a lifeless rock. Then, through processes we still don't fully understand, chemistry became biology. Simple cells emerged, then complex cells, then multicellular life. Through 3.8 billion years of evolution, life explored countless forms, from bacteria to dinosaurs to redwood trees. And finally, just a few 100,000 years ago, a cosmic blink of an eye, our species emerged with brains capable of language, art, science, and wonder. The atoms in your body have been on an incredible journey. The hydrogen was formed in the first minutes after the Big Bang. The carbon, nitrogen, and oxygen were forged in the cores of massive stars that died before our Sun was born. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all were created in the nuclear furnaces of stars or in the violent explosions of supernovae. These atoms have been part of nebulae, asteroids, and possibly other planets before becoming part of Earth. They've been recycled through countless organisms, bacteria, plants, dinosaurs, before becoming part of you. You are literally made of star stuff, connected to the cosmos in the most fundamental way possible. But we're not just made of the universe. We're the universe's way of understanding itself. Through science, we've discovered the Big Bang, mapped galaxies billions of light years away, and detected gravitational waves from colliding black holes. We've sent robotic ambassadors to other planets and landed 12 humans on the Moon. We've built telescopes that can see to the edge of the observable universe and particle accelerators that recreate conditions from the first microseconds after the Big Bang. Consider how remarkable this is. The universe evolved for 13.8 billion years, and then on at least one small planet, it produced beings capable of figuring out that history. We've discovered our cosmic story not through revelation or intuition, but through careful observation, mathematics, and the scientific method. Every culture throughout history has wondered about our place in the cosmos, but we're the first generation to know the true scale of the universe. This knowledge comes with responsibility. If life is rare in the universe, and we still don't know how rare, then we might be one of the few places where the cosmos has awakened to consciousness. The destruction of Earth's biosphere wouldn't just be a tragedy for us. It would be a tragedy for the universe itself, silencing one of the few voices in the cosmic dark. The search for extraterrestrial intelligence takes on new meaning when you understand the universe's true scale. With hundreds of billions of galaxies, each containing hundreds of billions of stars, it seems almost impossible that we're alone. Yet the Fermi paradox remains. If life is common, where is everybody? Perhaps life is incredibly rare, requiring a combination of conditions so specific that it almost never occurs. Or perhaps life is common, but intelligence is rare. Or maybe intelligent civilizations are common, but they don't last long, destroying themselves through war, environmental collapse, or technologies we haven't even imagined yet. The silence of the cosmos makes our existence even more precious. Until we find evidence otherwise, we have to consider the possibility that we're the only technological civilization in our galaxy, perhaps even in our observable universe. That would make us the only beings capable of appreciating the universe's beauty, understanding its laws, and preserving its memory. But even if the universe is teeming with life, our perspective is unique. No other beings will have exactly our history, our culture, our way of seeing the cosmos. The questions we ask, the discoveries we make, the art and music we create, these are our unique contributions to the cosmic story. The vastness of the universe also puts our problems in perspective. The conflicts that seem so important, the differences that divide us, they all fade when viewed from space. There are no national borders visible from orbit, no divisions between races or religions. There's just one beautiful blue world, a tiny oasis of life in an enormous cosmos. This cosmic perspective doesn't diminish the importance of human concerns. Poverty, injustice, suffering are all real and demand our attention, but it does remind us that we're all in this together. We share the same small planet, breathe the same air, and are warmed by the same star. In the face of the cosmic dark, our differences seem trivial compared to what we share. The future of intelligence in the universe might depend on the choices we make in the next few centuries. If we can overcome our challenges, climate change, nuclear weapons, artificial intelligence risks, we might spread life throughout the galaxy. Our descendants, biological or artificial, might witness the universe's far future, perhaps even finding ways to transcend the heat death we discussed earlier. Imagine civilizations billions of years from now descended from Earth life, spread across thousands of star systems. They would be as different from us as we are from bacteria, but they would carry forward the flame that was first lit on Earth. Every planet they terraform, every star they surround with solar collectors, every galaxy they colonize would be a testament to life that began in Earth's ancient oceans. The universe has given us an extraordinary gift, the ability to understand it. We can trace cosmic history from the Big Bang to the present. We can predict the future of stars and galaxies. We can even contemplate the universe's ultimate fate. This knowledge doesn't make us gods, but it does make us the universe's historians, poets, and philosophers. Every time you look up at the night sky, you're looking at your cosmic family tree. Those stars are your cousins, born from the same cosmic processes that created our sun. Those galaxies are distant relatives formed from the same quantum fluctuations that seeded our Milky Way. You're not separate from the universe. You're a part of it, a way for the cosmos to experience and understand itself. The true size of the universe, whether 93 billion light-years across or infinite, ultimately makes our existence more remarkable, not less. In all that vastness, in all those billions of galaxies, atoms came together to form you. You, with your unique consciousness, your memories, your dreams, your capacity for love and wonder, you are irreplaceable in the cosmic story. So yes, the universe is vast beyond imagination. Yes, we're tiny compared to galaxies and superclusters, but we're the part of the universe that knows it's vast. We're the cosmos contemplating itself, and that makes us central to the cosmic story in a way that has nothing to do with physical size or location. As you go about your daily life, remember that you're made of atoms forged in stars, that you're standing on a planet orbiting one star among hundreds of billions, in one galaxy among hundreds of billions. Remember that you're part of an unbroken chain of cause and effect, stretching back to the Big Bang and forward to the universe's distant future. But most importantly, remember that despite the universe's vast size and your seemingly tiny place in it, you matter. Your thoughts, your actions, your connections to others, they all add to the cosmic story. You're not just in the universe, You are the universe, experiencing itself from one unique and irreplaceable perspective. The universe is vast, ancient, and mostly empty. But it's also beautiful, intricate, and filled with wonder. And most remarkably of all, it produced you, a being capable of appreciating its vastness and adding your own chapter to its ongoing story. That's the ultimate cosmic miracle. Not just that the universe exists, but that it contains beings who can stand in awe of it, study it, and share that wonder with others. Look up at the stars tonight. Those points of light have been shining for millions or billions of years, and their light has traveled across incomprehensible distances to reach your eyes. You're connected to them through space and time, through physics and chemistry, through the cosmic story that binds everything together. The universe is vast, yes, but it's also intimate, personal, and profound. It's your universe, your cosmic home, and you belong here just as much as any star or galaxy. This is the great paradox and beauty of our existence. We're infinitesimally small in a vast cosmos, yet we're the part of that cosmos that can appreciate its vastness. We're a way for the universe to know itself, and in knowing the universe, we come to know ourselves. The journey to understand the cosmos is ultimately a journey to understand our place within it, and that journey has only just begun. If you are still watching, please subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one on the left side of the screen. What is the most powerful thing in the universe? In this video, discover the true scale of cosmic power, from supernovas and black holes to gamma ray bursts, quasars, the unimaginable energy of dark energy, and much more. See you there.